Lecture 19, Deformation and Strain. In the first lecture, we said that structural geology has three levels of study: geometry, kinematics, and mechanics. So far we have looked at geometry. In the next 2 weeks, we will look at kinematics, and more specifically, strain. Kinematics refers to the movements and distortions that occur during rock deformation. Deformation is the process by which the particles in the rock rearrange themselves from some initial position to the final position we see today. There are 4 aspects of deformation. The first one is the position of a rock particle as we see it today. The second one is the displacement of the particle from its initial to its final location. The third one is the actual path of the particle from its initial to its final location. And the fourth one is the dated path of the particle from its initial to its final location. In geology, we rarely know the path of deformation, and even less the dates along that path. Most often, we have some idea about the displacement of the rock particles. Here is a unique example of a dated path. The Hawaiian Emperor Seamount Chain. Each volcanic island formed above a hot spot in the mantle. Today, Hawaii is above the hot spot. The Seamount Chain shows the dated displacement path of the Pacific Plate. About 40 million years ago, the displacement path of the plate changed. We can think of deformation as consisting of 2 components. Rigid body deformation, which includes translation and rotation. And non-rigid body deformation, which includes strain. Strain involves either a change of shape or distortion, and a change of volume or dilation. Here are 2 examples of rigid body deformation. The upper one is horizontal translation, and the lower one is clockwise rotation. For each one, we show the initial and final configuration, the displacement field, and the path of deformation. Notice that the displacement field, which are vectors connecting the position of the particles before and after deformation, is different than the particle paths, which are the actual paths of the particles during deformation. Here are 3 examples of non-rigid body deformation or strain. Again, the initial and final configuration, displacement field, and particle paths are shown. Notice that for the first case, simple shear, the displacement field and particle paths are the same. But for the lower 2 cases, the displacement field and particle paths are different. We can describe strain as either continuous or discontinuous. In continuous strain, the strain properties vary smoothly throughout the body with no abrupt changes. A fold is a good example. In discontinuous strain, there are abrupt strain changes at surfaces or breaks in the rock. A fault is a good example. The study of strain is a branch of continuum mechanics, the mechanics of materials with smoothly varying properties. However, as we all know, geological materials are full of discontinuities. So why do we use continuum mechanics? The main reason is that the mathematics of discontinuous strain is too difficult, and at the appropriate scale, continuum mechanics is a reasonable approximation. For example, discontinuous strain as the one displayed in the figure to the left, can be approximated as continuous strain as displayed in the figure to the right. Thus, the concept of strain can be applied to brittle deformation. The success of doing so depends on the scale of observation. Strain can also be described as homogeneous or heterogeneous. Homogeneous strain means that the strain is identical throughout the material. After deformation, straight lines remain straight, and parallel lines remain parallel. For heterogeneous strain, the type and amount of strain vary throughout the material. After deformation, straight lines don't remain straight, and parallel lines don't remain parallel. In homogeneous strain, circles become ellipses in 2 dimensions, and spheres become ellipsoids in 3 dimensions. This is not the case in heterogeneous strain. These are 2 examples of homogeneous strain in 2 dimensions, on a rock slab with fossils, circular markers, and dikes. The deformation to the lower left is called simple shear, and the one to the right is called pure shear. We'll talk more about these terms later. Note that after deformation, parallel lines remain parallel, circular markers become ellipses, and the fossils obtain different shapes because they had different orientations before deformation. We can define the strain ellipse by two axes, the long axis, x, and the short axis, y. Based on these axes, we can describe the ellipse as shown in this graph. Field 1 corresponds to stretching of the two axes and increase of the ellipse area, field 3 to shortening of both axes and decrease of the ellipse area, and field 2 to stretching along x and shortening along y. The blue line in this field defines constant area deformation. In 3 dimensions, the strain ellipsoid is defined by 3 axes, the long axis of the ellipsoid, x, the intermedium axis, y, and the short axis of the ellipsoid, z. The Flynn diagram is a way to describe the strain ellipsoid. The axes of this diagram are the natural logarithm of y over z, and x over y. The ratio, k, as defined by this equation, describes several fields in the diagram. The line k equals to 1 is plane strain, where there is no strain along the y-axis. Ellipsoids above this line in the diagram have cigar shape, with x much longer than y and z. Ellipsoids below this line have pancake shape, with z much shorter than x and y. The mathematics of homogeneous strain is rather straightforward. One needs to look for a matrix, D, which relates the final, x', y', and z', and initial, x, y, and z, locations of the rock particles. This matrix D is known as the deformation matrix, and from it, we can calculate the strain. We will look at this later. We use homogeneous strain because it is simpler than heterogeneous strain. However, strain in rocks, like in this fold structure, can be heterogeneous. To get around this problem, we apply the concept of structural domains, which are regions of more or less homogeneous strain. We divide the structure, in this case the fold, into structural domains, and we look at how strain varies across these domains. To learn more about this topic, please read Chapter 2 of Flynns, and look at his e-learning module on deformation. And here are some questions.